Good afternoon and welcome, ladies and gentlemen. We now have time to start our session, so I would very much like to welcome you here. My name is Christian Hinz, business manager for digital physics at Mastermarket. I now have 10 years of experience with digital physics, and I'm happy to be your host for this session. So at the very first of this session, I'm gonna give you a short introduction to our session to digital core analysis. And afterwards, Lobel Danicic, your co-host for the session, will continue with the new technical features for digital physics. We'll have Professor Umar Fauzi from IT Bandung in Indonesia as an online speaker, talking about characterization of microstructures by combining multiscale material images. And afterwards, I will conclude talking about workflows for these rocks with respect to the oil and gas industry. And I would love to have a lively discussion about our roadmap as the final part of our session. Okay, so I'm going to start with the introduction. Please keep your questions for the workflows part. I'm happy to answer them there. So to bring us first on the same page about digital physics. So we want to answer questions about our reservoir in the oil and gas industry. So maybe for exploration teams, production, or research teams. So we want to understand the reservoir properties. In order to do that with digital rocks, we need to have a core drilled. Maybe a sidewall core or a core directly from the well bore. We need to prepare that into maybe a 1-inch plug and into a mini plug and do a micro CT measurement out of that, typically, in order to get a 3D image with the pore throats resolved properly so that we can do a digital rock analysis. Okay, having that sample can be input into GeoDict, where GeoDict like supplements and digitalizes special and routine core analysis and more to that. And with that, with GeoDict, you can save time and cost compared to conventional lab experiments. With that, you typically do the upscaling part. I'm sure we'll have more discussions about that part today in our session. The upscaling to the well log, integrating data into that, or feeding a reservoir simulator with properties determined at the pore scale. Okay, let's have a look at selected applications for these rocks. So we start off with a scan that's imported. Here's a 3D scan of a barrier sandstone, for example. We segment that scan into pore and solid phase, and the solid phase potentially into multiple mineral phases if that's relevant for your analysis. From there on, you can do different analysis. Let's start off with digital routine core analysis, which is quite automated in GeoDict. Another thing you can do is geometrical characterization, meaning like MSEP, and areas of porosity, and a lot of other characterization options for your rock. Another thing you can do is a digital SCAL with GeoDict, looking at relative permeability and arc exponents. Then there's geomechanics, looking at elastic properties, but also at stress strain curves with GeoDict. And finally, the entire topic of underground storage, talking about carbon capture onto carbon storage, but also hydrogen applications or thermal conductivities for geothermal applications. To give you a reference on whom we are working with, we may not show all of the users for GeoDict, but here's a selection. So you see prominent names like Shell, Petrobras, the OMV, you can see YPF. There's also Stanford University, and there's a lot more spread across the entire world. There's also large companies in other industries that you might have seen already in today's session. There's the automobile industry, there's battery manufacturers, there's filtration industry, and a lot more. First of all, I would like to introduce our team to you, to let you know with whom you're going to work with at Mastermarket. So there's me and Lobel, who are the Digital Rocks group at Mastermarket. Then we have Mike, who's responsible for our contacts in the Northern America. we have our manager Oliver and our CEO Andreas, who both have a solid background for digital rock analysis. And finally, then we have a lot more people in the company that are working with digital rocks, amongst others. So for project management, for development, software development, for technical support, but also for trainings. So there's a lot of people in the background. Might get in touch with one or another. You already have seen some of the stage today, and we'll see more in the tomorrow. Okay, and with that, I would like to introduce Lobel, your co-host for the session. Lobel holds a master's degree in reservoir engineering from the Montan University in Leoben, Austria. He joined Math Market 2 years ago, now being in the position of a junior business manager. In his position, Lobel acts as a professional point of contact for both technical and business tasks all around digital rock analysis for our contacts in the entire world. Okay, Lobel will present new technical digital rock physics features with a live demo. So Lobel, the stage is yours.
Thank you, Christian, for the nice introduction. Greetings, everyone who is with us here on site in Ramstein, and all of you who are joining us online. So first things first, I'm gonna drop from this presentation directly into GeoDict and start with something you may be familiar and show you the changes in 2025. So here I have one rock example loaded, and some of the things that are new in GeoDict 2025 and that come quite handy just at the first glance is the here track bar on the left side showing you the porosity as well as the solid constituents which was previously differently solved in GeoDict. So now you have a clear overview of different phases segmented in your digital rock model, and you also have the amount of porosity. This tooltip should be, by right-clicking, exactly possible to be copied, and then you can take the data outside if you need. Some other changes that came in 2025 also include the result files. So let me quickly open one where, for instance, now I'm not sure, do you see it on the contrast on the big sample, but on the screen for sure, now you can see the values X and Y of on plots. And also what you can do is zoom into the result files. Some of the result files, maybe this is not the best example, but here, if I zoom, it's much more clear, and some result files tend to be large tables, and then it may be even more beneficial to have such a feature. With that said, I can continue with the presentation and also show you more features that you'll find great for property prediction. I'll start with first improvements to FlowDict, namely to Lear solver in FlowDict for prediction of permeability, absolute permeability. So some of the challenges you are facing are, for instance, you have conventional reservoirs, sandstones, where the resolution you have of with your micro CT devices is mostly sufficient to capture the dominant pore throat sizes. So you can directly compute flow fields and then get the absolute permeability. In some other cases, such as more complex reservoirs, such as carbonates or shales, you can have much less of the resolution captured in your images due to the pores being in sub-resolution size. And in that case, the possible computations highly also are affected by resolution you have and what the resolution can capture. So now that I'm mentioning resolution, one of the things that we thought of in GeoDict was to include the so-called sub-voxel resolution. for the absolute permeability prediction. I'll try to give you an example how this works and why it's important. So let me turn on the pointer. Let's say we have one quite ordinary analytical example of two parallel plates where you have a 1 micron channel in between, and you know that the exact absolute permeability is approximately 28 millidarcies. And then if your resolution of image has only one voxel as a resolved pore channel in between, by direct computation previously, you would over predict the permeability by approximately 200%. And if you had the high resolution image, having approximately 10 voxels in between this channel to resolve it, the prediction in would be quite similar to actual value. And this highlights how much the resolution itself can impact the results. And what's now new in 2025 are the new error bounds for the mesh refinement and the sub-voxel resolution available that can numerically refine the grid for flow computation. Without getting into too much details of numerics at this moment, I'll just say that because, for instance, for one, our Sven Linden will give more in-depth talk tomorrow on the numerical side. I'll just say that some of the important application areas is, as I mentioned, tight rocks, low resolution scans, and for instance, also what we noticed for the simulation of filter cakes or mud cakes, where due to the way how the particles pack, previously the permeability could have been over-predicted. So with that said, now I'm showing you the one case study we did on the example of Berea sandstone, where the dominant percolation path diameter was around 4.5 voxels. So if we consider the previous example with two parallel plates, this would be somewhere in between having only one voxel or having 10 voxels for the resolution. And with that said, also the effect on permeability computed is not as drastic as being 200% over prediction. However, it's around 15%, we could say. So if we consider only the direct computation of permeability without any grid refinement and sub-voxel resolution, permeability predicted was around 1.5 darcies or 1500 millidarcies. And with the increase of the sub-resolution with this error boundary, we were getting lower and lower permeability to around 1390 millidarcies. This has one implication. As you're now having more computational cells, the runtimes are longer, as you can see. However, in some cases, the effect which you have on results is so tremendous that it's simply precision over the runtimes. So with that said, I would like to introduce the new novelty in terms of layer solver. So now, or actually how it was before, the velocity profile was always considering the no slip boundary depending on the middle size of the neighbor solid voxels. And now the no slip condition, which is required for precise flow modeling, is considering it directly at the interface. And this also we saw considerably improves the prediction of Fs-perm. And in addition to that, there is also the way how the equations for the discretization of the velocity profile are now run, so that exactly at this interface, now the parabolic velocity profile is used instead of the linear one, and this makes an even better prediction. With that said, let me jump right into GeoDict and from there we can go and do a short absperm prediction with both cases. I'll show you how the setup works so that you have it also as a takeaway for your future use. So as I previously showed, here is one small rock structure, and in the predict menu, I'll go to Flowdict and use the Stokes-Brinkmann solver. By clicking on Edit, we open the settings screen, and here let's start first with the initial case, how it was before. So without those grid refinements and no new no-slip boundary conditions. So first, under boundary conditions, I'll turn off the by now default values of the no-slip boundary condition, and I'm also gonna change the name to 2024, so how it was before, and go to Solver tab. Here under the Solver tab, there is the Advanced Options sub-menu available down, and by clicking it, the arrow, it opens, and here you can turn off the grid refinement, or turn it on, of course. And by clicking now OK and run, we have the predicted permeability of this small outcrop. It's around 1020 millidarcies. And now let's see how in GeoDict 2025, with the new improvements, how do they affect the absperm prediction. So I'm going to Boundary Conditions tab and turning on the pore solid boundary, so to no slip. And I'm gonna use the default, so second order for the velocity profile approximation with quadratic equation, and the sharp corner as well for interface boundary. And then I go to Solver tab, and here under Advanced Options, I'm for now gonna turn on the grid refinement method and also allow the sub-voxel resolution. So grid refinement is still considering the not sub-voxel resolution, rather just the way how the computational grid is refined, but under the still considering the same voxel size. And sub-voxel then does additional sub precision of the grid for the computation. Depending on the results you're getting, you may or may not turn it on. So it's also a bit of practice to seeing with your setups how the results come out. Now clicking on OK and run. Let's see the results. And I'm running this on my laptop, so it may be not as strong as your workstations you're usually using. So, okay. Let's see. Okay, so now we can compare the results. I'll hold Control and click on the previous result file. And here we can see that previously the permeability prediction of this sample was around 1020 millidarcies, and now it's around 704. So that's also considerable drop in predicted permeability. And yeah, is one way to even better predictions. Now I'll continue with the next improvement or new feature we have in GeoDict 2025, which is the upscaling MICP GeoApp. So I'll start first with the MICP, or mercury injection capillary pressure, and why it's important in first place. So as I'm quite familiar, you all know, and you all know it, material or rock properties highly depend on the amount of porosity and pore features, such as pore connectivity, pore sizes, and similar. And the properties from density, conductivity, and so on, or are highly affected. For that, the MICP experiment is done to actually do this characterization of pores and pore throats, volumes, and also getting the capillary pressure curve, important for the two-phase flow prediction. And now we also do it digitally in GeoDict. Here you can see the end stage of one digital MICP experiment in GeoDict. In the light gray, I hope you can see it on the big screen. In light gray are only the pores saturated with mercury. So in the first part of the structure, there is no solids visible. And in the back, you can see in dark gray the solids and also the saturated, mercury saturated pores. Now I'm gonna quickly play the animation, how this looks like when computing it in GeoDict. And on the right side, you can also see the development of capillary pressure curve up to the final point. So this can be done when you have your pores resolved with image, or at least resolved until a certain pore throat size. But oftentimes, you may have the larger scans where you don't have the explicit resolution of finer pores that highly affect the MICP, or which MICP shows that are in your sample. And for that, it may be impossible to directly predict the MICP curves. And to do so, there is now a new workflow in GeoDict 2025, which starts with image segmentation of a large scale sample, so into pore space, which can be resolved, and different poros, we call them solid phases, which have different amounts of porosity in the in this example. Then what we suggest is having sub-samples taken out of the larger sample, which can be either scanned with higher resolution micro CT, or also directly used in MICP experiments to get the actual pore throat size distribution and capillary pressure curves. When you have those sub-samples, you can populate the large model in GeoDict, and with the capillary pressure curves for each of the porous regions, the new solver in this GeoApp combines them with the consideration of their connectivity checks. So meaning when mercury starts invading the, for instance, in this case, this fracture, it would go in the fracture, and then at certain saturation start entering either of porous phases, depending on connectivity and the capillary pressure curve of each of the porous regions. And yeah, so this is one of the first steps we have in the upscaling of two-phase flow properties. So first, we started with the, let's call it simpler experiment, which is MICP, and we plan to build upon and also do the capillary pressure curve upscaling for other more complex systems, such as oil and gas, and also predicting the relative permeabilities on the large scale samples. With that said, let me also jump now back into GeoDict, where I'll start by, first of all, changing project folder, and then loading the structure, the large structure. So here we have one large structure, and let me turn on the pores. They are in black. So what we have resolved are some larger pores and fracture in the middle. And yeah, as you can see, also some pores on the top. Now to use this new GeoApp, we go under the predict and set predict, which is our module for everything related to capillary pressure and two-phase flow. And then under the two-phase flow GeoApps, there is the upscaling mercury injection capillary pressure GeoApp. Now by clicking on edit, we can set up the properties for this computation. So let me move this window here to left and click on load GDRs to assign Capillary pressure curves to porous materials. If we assume that we have the subsamples that have direct resolved pore space, where we manage to compute the MICP with GeoDict, we can load those results, and which I'm going to do now to populate each of the segmented porous regions. And there is now one more option, which is the breakthrough of each of the porous regions, which depends on one end on the pressure that is in the sample. And this sample is, I can say, tracked with the capillary pressure curve via the saturation. So there are two options, either with Tomer model, if you have it as part of your license, or with this saturation for the breakthrough to have it as well then for how the capillary pressure or mercury will develop in each of the porous regions. For each of the porous regions, there will be different entry pressure depending on the saturation. And now I can click on run. So it's only a few options to set, and we'll get the upscaled capillary pressure curve. While the simulation is running, I may ask, are there any questions both on-site and online? So we can start the discussion of the first part. Okay, then we can quickly jump to results and see the combined capillary pressure curve, as well as the pore throat size distribution for this particular sample. So with that said, I would now go back into the presentation. We had a Q&A, and start quickly with the next improvement and a new feature in GeoDict for the ERP, which is the advection diffusion and reaction solver. So first, in 2025, we started the modeling of the transportation of one concentration field that can be, for instance, CO2 or other solutes. So transport of it by advection and diffusion as the continuum phase. The way how this works is first by computing the Stokes equation to get the actual flow field, and then by running the advection diffusion equation, where it considers the concentration of the inflow solute, and based on its, for instance, diffusion property and the computed flow field, there will be the transport in transport in the porous medium. What is further planned is inclusion of multiple solutes, so different concentration fields, which would also involve different types of reactions, which in the end would be, for instance, used for continuum way of modeling the reactive transport. The new approach also allows for coupling with thermal or mechanical effects, which is a new feature in the GeoDict module. With that said, I'm gonna jump back into GeoDict to show you how the setup for this actually works. So I'm in GeoDict, and I'm gonna load the structure. Again, the small sample here. And oops. First of all, we go in the predict menu to Adsorption, and here there is now the new field called transport concentration field. And here you can also set the properties for the simulation by clicking on Edit. I already predefined some of the properties, for instance, of the which for some of the settings you would expect for the transport of CO2 as a solute in air. So here, some of the properties you need to select is what are the actual transport mechanisms involved. So is it only advection or advection and diffusion? What's the concentration at the inflow side of the solute, or the concentration of a certain gas or other fluid that is transported? And then there is the setup of the inflow properties, either the pressure drop or mean velocity or flow rate via volumetric rate and area. Now also you can see here the addition of new boundary conditions for flow that come with Lear solver. And here under the constituent materials tab, you can set up the diffusion coefficient of the this inflow concentration into the fluid that is currently present, in this case air, in the example. And then under the transport options, you can for now leave everything as is on default. And for the flow solver, this is same like in the flow declear, as I showed earlier, with also the grid refinement and other options. Now by clicking OK and run, we can run this example. I think we are getting short on time, so I'm gonna speed up, and I can directly open the results. I have them somewhere here. Yeah. So the runtime is around 4 minutes. It was around 4 minutes for this example. For the results you currently get, it's the different dimensionless numbers showing the advection, diffusion, and reaction in this example. And there is also quite important breakthrough curve showing how does this concentration move from the inflow to outflow region of the example. And also different statistics on the storage, let's call it that way, of the inflow of the solute in the porous medium. So with that said, once again mention that in 2026 there will be the addition of multiple solute species, so different, for instance, gases, and also the coupling with other effects. Now we head to one example that is not directly digital rock related. It's more oil and gas or energy industry related, which is the adsorption for carbon capture and storage. And here I'll focus on carbon capture part, so not the storage, rather the first part of the equation, which is capturing carbon at large point sources, which can be either industrial power plants or direct air capture plants, where carbon from, for instance, air is captured on the activated carbon pellets due to the high adsorption affinity on the surface of such reactors. And here you can then use, for instance, GeoDict for modeling those geometries and seeing how different, for instance, packing or length of the reactor affects the adsorption of gas, in this case CO2, on the surface of activated coal. Here is the look on how does this actually is visualized in GeoDict, and what is also the end result is the breakthrough curve, where in ideal case we would see the for instance the frontal movement, so meaning as the gas is injected, it fully saturates, which is of course not possible. It's the idealistic case, and the optimization with either the pellet properties or the geometry can refine how the breakthrough curve occurs. And I'm jumping back in GeoDict. So first, I'm gonna move to other folder and open one such geometry, the reactor for the adsorption process. So I may also now change a little bit the color just to highlight. In this case, we have the steel container, and inside the pellets of activated carbon or sorbent, which would react with this inflow fluid stream. To use this adsorption modeling feature, we go under the Edict. So I already have it open, and I'm going to show once more. Predict Edict, and then Advection Diffusion GeoApps Adsorption. We can use this feature by clicking on Edit and setting up the expected simulation parameters. So this would be the duration of the process, the concentration of gases, their diffusivity of the this adsorbent material on the adsorbent or activated coal, and also properties such as density and porosity of the adsorbent phase. I can load one setup I did, which would be for the, for instance, 3-batch, few hours, 1.5, 2 hours experiment, which mimics the actual processing in real plants for the activated pellet, and also the concentration of CO2, which is, for instance, present in the air, in the airstream, if we speak of direct air capture, and other properties such as diffusivity in the pellets or in the air of the carbon dioxide, as well as the experimental conditions are here set. So the ambient conditions, and also the properties of the pellets themselves. So what's their density, porosity, and permeability. For actual capture of the carbon, we have the different types of models, such as Langmuir and Todd, and also table input, so which show how active are the surfaces on the pellets. So what's the actual affinity for capturing the CO2 for on their surface along the adsorption process. And now by clicking OK and run, we would run the results, which again, I'm gonna skip and go directly to results. So the main part how for now the modeling of the geometry of this reactor would go is through observing the and quantifying the outflow concentration with the breakthrough curve, and seeing how does the load per each layer of this reactor change with the CO2 stream. With that said, I'm gonna go further with the job queue system for digital rock physics applications. You may have heard also this morning there have been quite some advancements in the GIC 2025, so that the job system is now more reliable and gives you better, let's call it management options for the prioritization of different queues and so on. So I'm gonna skip the intro part, you heard about it, and just say that, for instance, job queue is quite good when you have multiple GeoDict users and one strong workstation to compute the different jobs, and it's quite easy to run it. So I'm going to show it in a moment, and it gives quite a good degree of freedom on setting the priority or getting the results directly from the job system. So let me go into GeoDict once more. And I'm going to load one structure. And first of all, we should start the job queue. So let me go to Manage Job Queue Server and start the server. On, and it should be running. Yes, it's running. Great. So first of all, I'm gonna delete some of the previous jobs and start with the blank state. Okay, so job server is now running. It's running on my own laptop. Most of the time you would do it on, you would start the job server on one of your workstations and send the jobs from your laptop to this workstation. So in this case, it's just for an example. And let me start first by going to one of the simulations, such as maybe computation of elastic properties of rock in the elastodics module, so with effective stiffness, which would give us the prediction of Young's modulus Poisson ratio. For now, I'm just going to use the default settings and go ahead and click on Job Queue. And now the window will pop up, which shows the project name. This is based on the project folder in GeoDict which you currently have open. And then there's this prefix name, so basically what type of simulation you're running. And also if you want to upload the current structure, which I'll click yes. And also for some cases, the whole content of the project folder. For instance, if you want to run multiple different structures or also use some settings and so on. So for now, I'm gonna keep the default and say that the selected machine will be used. So in this case, it's my own laptop, but you could also have more job servers running. And click on Run. Now the process is packing the structure as well as the settings of the simulation and sending it to the job server. Simulation status is shown here, and you can also see more or sort differently the jobs running, which I'm going to show in a moment how it looks like when I start another simulation. So let's go to FlowDict. And also, for instance, for permeability computation, just click on job queue here and see how the setup goes and how it looks like in the job manager. So let's click on run. And now we have the queued simulation for absolute permeability, while the effective stiffness computation is running. The simulation that is already running cannot be, let's say, reprioritized by the second simulation. So it will run until it's either stopped, which I'm going to do in a moment, or once it's deleted. I'm also going to queue one more simulation, for instance, the one shorter, so such as open and close porosity computation. And clicking on job queue will set up the job. And now I'm just gonna show how, for instance, the prioritization goes. So there is the selection of the priority by the arrows, which can be done from here, or we could also go ahead and stop the currently running simulation and see how the results are later reached. So I'm gonna terminate this one and also delete this job. And we have the short simulation, so I'm running out of time, completed. And now how you would get the results is by clicking on download results. And from here you can select which files you need. So you may only get the result file, or you can go ahead and download all results. So I'm just gonna click on OK and select this folder and download the results. So that's it. And I can now just quickly open the results directly from the window. And here are the computed properties from this job. So that's it. Please go ahead with other questions you may have before the next session.
So my talk will be all about workflows for the oil and gas industry. But what do I mean by that? So I want to look at many different features started here amongst all the different topics that we've tackled earlier. All right. So I'm going through all the different topics here and present the features that we have for each. And before I do so, I would get back to our topics about scales. So what scales are we tackling in GeoDict exactly? So we're looking at the pore-scale in GeoDict and at the core-scale. So the pore-scale, as we've seen, there's nano-resolution systems of pore spots. There's micron pore systems, depending on the rocks you're looking at, if it's sandstones or shales, or even carbonates, which are a lot more complex if it comes to the number of magnitudes and pore sizes. And then there's the core-scale, where we need to tackle the entire story a little differently because it's like unresolved scales that need to be fed with properties, similar to reservoir simulations in that sense. Okay, there's of course also the scales about log scale. There's a study from Gordon Burmester, for example, published as a conference paper on how they do this integrated upscaling, and there's the reservoir models that need to be fed with GeoDict data, amongst others. Okay, talking about scales, we also need to talk about when do we need to do upscaling, which is a topic about homogeneity and heterogeneity. So coming first here to homogeneous rocks, having a homogeneous rock, you can do a core plug, a mini plug, get a micro CT out of it, predict the properties of the rock, and can fairly assume that these are representative for the core that we are looking at, assuming it's homogeneous. If we go to heterogeneous rocks, however, the story is a little more complicated. So we need to identify different regions or rock types or phases, however you want to call it, in the at the core scale, and then do subplugs for each of the different regions that are representative for that region, do the entire digital physics workflow for each of them, and then we need to find a way to do the upscaling. So we need to have a core scan segmented into different regions, feed it with properties that we've computed, and do the upscaling. That's what we've discussed about with the Darcy solver just right now. That's what Lobel has shown about the MSCP upscaling, and that's also what we want to have for relative permeability. Okay, which is upcoming. Okay, with that, let me get back to the digital physics features. First off, segmentation. So segmentation is about importing your data. You're importing any kind of data, and if something's missing, it's like image stacks of diagram files, we'll take care and implement it in the software. So you're importing your data, then typically you're doing some filtering to get the noise out and sharpen the image. Like here you can see for a carbonate sample with a lot of noise on the left-hand side, with a non-local means filter going over it and reducing that noise while still keeping all of the edges sharp in order to have the segmentation step a lot easier. So for the segmentation step, there's various methods. For example, you can do the manual labeling, painting each of the different phases that you identify with for different ID phases, and then do the algorithms, do the segmentation for the entire 3D rock. So here, for example, a random forest, which is one of the popular methods. There's also other options in the software to do so. There's one example that was also shown earlier today about enhancing the image quality that we've done in collaboration with Vasanthi Chandra from Chaos University. So there we did like a deep learning workflow. We took scans of short exposure time and long exposure time, with the long exposure time scans being the high quality scans that represent here the ground truth data. We trained a model with these pairs of data and applied them on a carbonate sample with a low exposure time, so with a low quality, and reproduced a high quality from that scan. So that's what you've seen earlier today as a slide already. Going from the high quality scan with a long scanning time over the low quality scan with a short scanning time onto a low quality scan with a high quality image by applying the AI workflow here, or the trained model basically. Another topic is quality assurance. So how can we check that our DigiRock has a good quality for DigiRock analysis? So there's several measurements, for example, looking if your rock has a representative elementary volume. So how can we check if there's an REV size? There are some publications from Nishant Saxena from Shell, for example, where he recommends what the REV size is for a sandstone for absolute permeability determination. So that's something that we have in the software as a single-click feature in order to help you understand the quality of your rocks. That's the one thing. Other thing you want to look at is, are the pore throats resolved properly? And there it comes to different things. Are you certain enough that your data is good enough to provide you with a result representative for your rock? So there's two things of uncertainty. There's the segmentation uncertainty that comes down to your segmentation. And then there's the numerical uncertainty, which Saxena et al. Have shown that there's a uncertainty coming in the lower the pore throat diameter sizes are in terms of voxels. However, as Lobel has presented earlier, and as we are also seeing in the plenary stage, We have the new feature in GeoDict 2025 that tackles this numerical uncertainty by going to sub-resolution grid cells, and thus giving you a numerically correct result for structures that are not like with 10 voxels in pore throat diameters. So this is really helping you out and improving the quality of the results. So that's the two things that you need to be aware of. How good is your uncertainty or certainty, and what's the things you need to set in the software as Lowell presented to get things right if you have low pore throat resolution. Okay. There's another thing about quality control. So if you're doing lab work, you don't want to have fractures in your rock that you can't see, that you don't expect there. So you can do like automated scanning of your samples in order to determine if the sample is viable for lab analysis, lab work. So that's something that you can also do with the software. There's like fracture identifications in GeoDict to do this automatically. From that, I would like to go to the next topic, digital routine core analysis. There's an automated tool for that in GeoDict. All you need to do a digital routine core analysis is loading your sample, choosing the application, the feature, selecting the properties you want to have, and just simulate it, and you will get results obtained, visualized, and automatically stored in a PowerPoint report file that tells you all you want to know for digital routine core analysis with GeoDict. So what's all in here? So for example, there's porosity. Now looking here at a Gilderhauser sandstone, here's the solid framework. You can see the grains. In the center image, you can see the pore space resolved with the grains transparent here. And on the right-hand side, you can see basically the isolated porosity, more or less, in green and yellow color. So all of the porosity that you're seeing here is basically, most of it is accessible porosity for that sample. So you can get like accessible porosity and isolated porosity. Okay, you can do a pore identification in GeoDict. So of course, there's porosimetry where you get pore throat size distribution. But there's also a pore identification, which uses a watershed in GeoDict and fragments the entire pores into like different pore bodies and gives you equivalent diameters as a pore size distribution out of it. As a visualization, you see the different pores in different colors for the Gilderhauser sandstone. Part of the routine core analysis is also the absolute permeability. So you can predict the absolute permeability across scales. So using the Stokes solver typically can also be extended with the Navi and the Brinkman terms. And we have a Darcy flow solver for unresolved structures, determine we are giving in matrix permeability. So basically we can do upscaling from nano to micro to whole core scale. Of course, there's difficulties as we've just learned. But there's something that can be set up. Okay, so what else to tell about absolute permeability in GeoDict? The solver, the GeoDict LAR solver, it's basically faster than anyone else. So you can see here from the runtimes, it's 15 minutes with a 99% accuracy to get the result on a modern workstation with 16 cores or processes. Okay, so you get accurate and reproducible flow results. And now in GeoDict 2025, we also correct this numerical overprediction of the velocity in narrow pore throats. That's with the uncertainty that I've just told before that can now be tackled. Okay. Next topic would be the geometrical characterization. So there's mercury injection capillary pressure in GeoDict. So you can compute the digital MICP, which considers the unresolved porosity of micro-CT images. You can also validate the GeoDict result by comparing the digital with a lab MICP. All you need to do is take care that you plot the x-axis versus total sample volume, which is giving you a nice fit of curves as shown here for lab data from Steffen Berg et al. 2016 paper, where we show how good it fits. also not, basically after the paper. Then we can also estimate this unresolved porosity that we have in a rock. So we're adding a Tomer fit. I'm showing you here in the red curve the GeoDict data and the Tomer fit as the line. That's showing that we're predicting the unresolved porosity for your rock, which is here, for example, like around 2% of the porosity that's not resolved in this example. You can also identify not just pores, but also fractures in GeoDict. So you can separate the individually identified pores also into small pores, into large pores or caverns. You can also separate them into fractures, as shown here for this red fracture system. With that, you get all the statistics that are along with that. Diameters, sphericities, orientation. So meaning you get a fracture orientation plot that of course you need to kind of consider the orientation of the sample in your reservoir. Furthermore, there's grain identification. I'm running a little out of time, I'm sorry for that. So you can identify individual grains as shown here with the colors. So giving you the grain size distribution as a plot as shown here. Now let's have a look at digital SCAL. So we're using direct numerical simulation for solving two-phase flow. So we simulate directly in the voxel geometry. For that, we use this upgraded dynamic pore morphology method, which is a morphological approach with dynamic fluid interfaces. So we can compute the primary drainage and a subsequent imbibition, or just the entire hysteresis cycle. So here on the right-hand side, you see a sample, primary drainage, capillary pressure curve, and a subsequent imbibition curve. We can also see that it's going here to negative pressures, which I'm going to explain in a minute. And in this animation, you can basically see a primary drainage with the oil being injected from the bottom and displacing the water phase. So that's something you can compute in GeoDict and also visualize and animate for any type of presentations that you need to do. Okay, to get into these negative pressures, we need to also consider spontaneous but also forced imbibition. And for that, we need to simulate the aging process. So the aging process is typically done in the lab. And to get that into the GeoDict, into the workflow, you need to do this digitally. So we're simulating the aging process so that you can also not only do water wet systems, but also compute relative permeability for mixed wet systems. On top, you can compute gas trapping curves, which is verified here against the land paper. There's also a study out for that one. And finally, more or less looking at enhanced oil recovery with like secondary recovery here. So you can simulate the water flooding and the entire hysteresis cycle by not only doing the primary drainage curve, but also the spontaneous imbibition, and on top the forced imbibition part here, which gives us into negative pressures and allows you to mimic the water flooding process. You can also compute the secondary drainage here and get the entire hysteresis cycle with GeoDict. Which brings us to relative permeability. So you can compute the relative permeability curve. You can investigate the uncertainty. And here we're basically showing one publication from Pitt Arnold from Montana University in Leoben, which has been supervised by Steffen Berg from Shell and Holger Ott from the university. Okay, so what are you seeing here? You can see the oil relative permeability curve and the water relative permeability curves. I'm showing a parameter study for our simulating aging tool. So he kind of stresses out what we have implemented, finding a good value for matching the experimental curve. So the experimental data is the red squares here for the oil relative permeability and the blue squares for the water relative permeability. So this is the experimental data, and he matches quite well with the GeoDict computations here. setting certain parameters as published. Okay. With that, I would like to go to Archi exponents. So you can predict the resistivity index from a primary drainage computation, get a resistivity index curve out of it, which provides you with more thorough data points than a plain Archi equation would give. So in blue, the Archi equation, and red, the data points that are computed. And to correct that, as just discussed, we implemented thin water films. So if you look at a sandstone here, zoom a little in, and in between these quartz grains and the oil phase, we know that there's a thin wetting film, a thin water film that adds to the conductivity of the sample, and that's what we add here, allow the user to give as an input, like 20 nanometer thin films or whatever you think is fitting here, in order to consider that and correct the resistivity index and also the saturation exponent results. So in a comparison for that barrier sandstone, you see in blue curve is the resistivity index without consideration, and in red, the corrected one with consideration of thin films. Okay, I need to speed up a little. Geomechanics. So you can predict the overall mechanical properties of reservoir rocks, getting Young's modulus, Poisson ratio, bulk, and shear modulus. So you're getting elastic properties. You can also set a compression simulation with various kinds of setups in order to obtain stress strain curves. So we are looking into that right now with like more detail. I believe that right now. Then there's something about upscaling you can do for elastic properties, which is published by Stanford University. There's something about elastic properties of organic rich source rocks, which again brings us down to nano-resolution scans. There's published data. And there's also what you can do if you have the effective stiffness. You can also compute PNS wave velocities and acoustic impedance using the correct equations for that one with the GeoDict results. We're looking into getting that validated right now. Okay. So I still have 1 or 2 minutes for underground storage. So for underground storage, if we talk about CCS, carbon capture and storage, it starts with carbon capture. So we now have adsorption in the software as presented by Lobel. So this is something you can do. You have seen the setup in GeoDict. And yeah, as a next step is controlling like storage of carbon dioxide. You can do different things in GeoDict to understand the CO2 sequestration. You can inject CO2 as a fluid phase in order to compute residual trapping with two-phase flow, as we've just looked at. Or you can simulate the injection of a CO2 saturated brine and compute mineral precipitation and dissolution, which brings you to like dissolution of pore cement carbonate phases, for example, or which brings you mineral trapping, whatever the geochemistry of your reservoir brings in into the simulation. So you can set the entire complexity of or most of the complexity of your reservoir formation fluid into the GeoDict software so that geochemistry is handled. If you're having mineral precipitation dissolution, you can characterize these rock changes up in the CO2 injection. So you're not only getting the change in porosity, but also the change in absolute permeability, or even the change in relative permeability can be computed on that. And if that can be done, you can also look at the elastic properties, how they are changing up on the changing composition of the rock at the surfaces. Okay, so quickly how that is done for reactive transport in GeoDict. So if you have an input geometry, which is here a coarse-grained carbonate sample, you can compute the flow field, the advection. On that one, we are computing the particle transport. So we're simulating advective and diffusive motion of particles. We use them in a Lagrangian approach to compute chemical transport. I mean, now we have also the new advective diffusion solver that could handle that differently, but that's another story. And with that, we can like attach or couple to a geochemical calculator that computes reactions at the water-rock interface in order to understand, for example, in an acidizing treatment simulation, how the carbonate is dissolved upon the injection. What you get out of it is in the post-processing, a porosity permeability plot, backlet numbers, reaction rates, Dampiller numbers, and all the sort of things. Okay, and with that, I'm in the question round. I think we're almost at the end, but maybe we have time for 1 or 2 questions. Okay, thanks all for the questions. I mean, we're out of time, basically. So to have anyway the discussion, maybe let's call it a start and not an end of the discussion. I'll quickly show our roadmap to give you an idea on what we are planning to work for the next release and the release after, and even the near future afterwards. We are planning to do some things for AI, for thin section analysis, for digital SCAL, for geomechanics, also for direct air capture, for underground storage. So there's a lot of things we're kind of looking and focusing at right now. And we'd love to hear what are your needs. What's the market trends that you see for the future? So let us know either in the chat, in the survey, or in the audience, maybe in the poster session that is taking place on site in a few minutes. So I'd love to have your feedback at some point in time.